Spanish ecosystem from the startup Kilimanjaro. Albert has a background more than 20 years in the tech industry. Your expertise is from, come on stage, Albert, please. Let's give him an applause. Thanks for staying with us here.
Hello.
Albert, your expertise is in AI, blockchain, you name it, and now quantum technology.
Now.
And you're the Chief Business Officer for Kilimanjaro, and you'll talk about Quasic. What that is, that beautiful word, I'll let completely up to you. The stage is yours.
Okay, thank you. Thank you very much. Welcome all. So it was 2019 when one of our co-founders, Paul Forn, actually won an European project for Flux qubits and using them for the coherent analog computing. So that was the very beginning of our company. 4 years later, we have built a chip that we have this unique approach in the quantum computing space to actually perform this analog annealing, but also quantum simulations. And I'm going to show you how is our approach different of what you have been seen so far. So basically, kind of an intro. Probably you've seen many of these, but the current computers has many purposes. There's many use cases that we want to solve. It's namely chemistry, new drugs discovery, logistics. But we are facing kind of the limit on what we can achieve and run into those computers. Either power, we need kind of more runtime, and we want kind of more resources. Recently, there's also like the sustainability that is also important in when you run and when you model your AI algorithm, right? So there's also this sustainability, let's say, limitation that we're gonna need to get track for that. There's then the quantum ecosystem and quantum computer, which a few benefits that we probably, you all know that, right? So there's why we run quantum computers, mainly, I mean, this is like a super simplification, but mainly because we want faster solutions. And so everything that, a new algorithm that can run the same problems, we have even better accuracy, and this is important in chemistry. But recently, as I was saying, there's also like the sustainability is also an important issue. I can run the same with lower cost, and this is let's say a new tax that may come in, and we need to consider also that. So this is kind of the general overview of the quantum technology. Now our approach, as Mira was saying, is we build Quasics. We build quantum ASICs. So usually, if you probably heard that in the classical world, but we do that in the quantum computer. So basically, we develop quantum application specifics, and we pick a use case, and we map and we build our quantum chip as close as that use case. The reason being is we all want to be general, but we know that it's going to be a long road ahead. So that is like, okay, let's build something very useful at the very beginning, in a short time frame. So this is our approach. What are our ingredients for doing that? 3 ingredients and one approach. The first ingredient is, instead of going digital, we are moving into the analog space. So we encode the problems into a Hamiltonian instead of a quantum circuit. This allows us to also bypass some of the error corrections that the digital quantum computers already has. So digital computers, they have some errors, and we, even us, are working on the quantum error mitigation, quantum error correction. But they do have that. And even in the description of the problem. So when you discretize a problem, you also have there a possible error. In the analog world, you have a continuous way of encoding. And kind of this is kind of the roadmap that we foresee, right? So we are moving to the classical world, into these fault-tolerant computers in the long run. We are in this niche area, and we're working on several solutions, let's say, to go into this fault tolerant. That fault tolerant, it means that we are able to be noise-free quantum computers, but also, like even the algorithms that really make sense needs many number of qubits, right? So this is also even an enduring issue that we need to overcome in order to get into this fault tolerance and actually provide like this quantum advantage. Now you probably know who this guy is, Richard Feynman, one of the fathers of quantum mechanics. And there's this famous quote that says, nature actually isn't classical, damn it. And then in Kilimanjaro we say, not digital, damn it. So basically it's like, if we want to mimic nature, nature is quantum and analog. Okay, so let's build a system that mimics that as well, right? So this is kind of our approach in the analog space. That's why our first ingredient. The second one is, I told about the work that one of the founders was doing in flux qubits. So these type of flux qubits let us kind of increase the coherence time of this execution of our programs. So we want to put the focus on the quality instead of the quantity, right? So we want to build those chips that really are coherent, so then we have the quantum properties throughout the execution of the program, of this analog program. Now this is one of the characteristics, and we are working for that. So instead of going and start scaling up quickly, okay, let's focus first on small chips. And finally, we all want to be universal. For doing that, what we need is the quantum interactions, not only like the Z-Z interaction, but also like other type of interactions that let us encode arbitrary Hamiltonians. So this is also like an R&D line that we are moving to get into these encodings that is necessary to go universal. But we're gonna do step by step. Our approach is unique also in the sense that we are co-designing the chips with you guys. So we have an internal team, and we're gonna build our first prototypes. But when we are gonna release that, what we need is the feedback on what's the next evolution of those chips. What is the use case that you really need to solve? And then let's see, what power do you need in the chip itself? So then we can provide that solution. And maybe it's not about a number of millions of qubits, but also it's because you need that kind of topology in the chip, that kind of interaction, that we can do that. So this is the co-design approach that we do. We're gonna release next year our first quantum chip. It's gonna be a 5-qubit chip. It's gonna be for analog. And then with a nearly all-to-all connectivity with the chip. But yeah, then this is the question. What do you want to run? We have built this for some particular use cases, but what we want is to encourage you to interact with us and also to understand what's the needs, so then we can evolve this technology for the future use cases. We're gonna start small, but then every chip needs to make sense for this joint roadmap. This is one of the prototypes, and this is one of the verticals that we have worked. It's gonna be on QuASIC for chemistry. We have this internal project funded for the EIC, and it's called Rocket, and this is our first prototype for next year. And as I was saying, like, this can be kind of one of the paths. Don't take these molecules as a state, but we are working on what's the evolution in terms of chemistry for our roadmap. So we will start like super small with some basic hydrogen molecules that you can simulate with your laptop, but in our chip, using the quantum properties throughout this execution, we can replicate those molecules. So what we want is to work, and actually we are partnering with an institution from India, CQER, to work towards this roadmap on chemistry. And this is one of the verticals that we are working on. As I said, like next year, start working on this industry, and then let's work into other industries that really make sense, that we can start small, and then we can increase the topology, the type of chip, the use case that we can solve. Even, I mean, optimization problem requires many qubits, but with better encodings, maybe we can tackle the same with less qubits. So these also are lines of investigation that we have in-house that we can work with you. Ideally, we all want to be universal. We want to solve all the problems. So this is what we envision. Basically, we want to master nature to advance humankind. You can find me in the booth. We are Kilimanjaro. I'm Albert Solana. Happy to answer any of the questions you may have.
Thank you, Albert. And I'll have a look if there are questions in the room. I actually have a question for you.
Sure.
You said that Quasic will be on the cloud next year. So how does the access work? Is it your cloud, or are you going to be in AWS? Like, how can people access it?
In Kilimanjaro, we are a full-stack quantum computer. So we provide also the cloud ourselves. The idea is we can provide a user and a key for accessing the cloud, and we provide a set of libraries, you encode your algorithm, and you run it directly to ourselves. We do plan also, and we are already engaging with other cloud providers. So then, we can, let's say, democratize more that kind of the access to our cloud system, but we do want to interact one-to-one with our users, right? So get feedback and then improve better.
Thank you. Any more questions here? No? Then, Albert, thank you so much again. Thank you for being here.
Thank you.